What up? Homework 4 video. Let's do this. Sketch a portion of a function whose derivatives have the following characteristics. Okay, so combining the last two lessons is what we're doing for this class. Understanding f prime is positive. That's the whole f prime being positive tells me f is increasing. If f double prime is positive, that tells me f prime is increasing, but more importantly, f is concave up. So F needs to be increasing concave up, increasing curving upward. That would be a portion of F. Okay. F prime is negative, F double prime is negative. Okay. If F prime is negative, then F is going down. If F double prime is negative, F prime will be decreasing, which means F is concave down. F is decreasing, concave down. Decreasing, concave down would be like that. F prime, positive, F double prime, negative. F prime, positive, F increasing. F double prime, negative. F prime, decreasing. F curving downward. Increasing, but curving downward. That would be F. Okay? Sign of a derivative tells me if the previous thing is increasing or decreasing. So f double prime sign tells me f prime increasing or decreasing. If f prime is decreasing, you got to be concave downward. F prime negative, f double prime positive. F prime negative, f is going down. F double prime positive, f prime is going up. If f prime is increasing, f must be concave up. So I'm going down, but I'm concave up. Going down, concave up looks like that. Okay, f prime is negative and increasing. Ready? Watch this. This is when it gets a little bit tricky, but let's see. We'll start with f prime being negative. That means f decreasing. Okay? F prime is increasing. I'm going to go over here to another number line and say f prime is increasing. Well, that's here in the bottom of my second derivative sign analysis. F prime increasing means F is concave up. So I'm decreasing concave up. Decreasing concave up looks like this. Okay. I want questions about F increasing at an increasing rate. Stuff like that. I don't really have those. I'm going to put them in here. The last two I'm going to change. F prime positive means F is increasing. F prime is decreasing. If F prime is decreasing, that means F double prime is negative or F is concave down. Increasing, concave down. Last two I'm going to change. So I'm going to say like F is increasing at an increasing rate. Okay, this is really the same question as what was originally asked, but I want you to be familiar with this because it's a little bit different. Okay, so if I'm told F is increasing, okay, cool. That means F prime is positive, F is going up. If F is increasing at an increasing rate, that means the rate at which we're increasing is increasing, or F prime is increasing. If f prime is increasing, f double prime is positive, f is concave down. Okay? Going up, concave down, same as the last one, actually. Uh, whoa, sorry. Concave up, positive, increasing. Going up, concave up. Okay. The last one I'm going to change as well. I'm going to say f is decreasing at an decreasing rate. Okay? It's the same as the original question, but I like this because if everybody just reads this and tries to graph it, they make mistakes. They're like, oh, we're decreasing, but the rate at which we're decreasing is decreasing. They think it looks like this. But this is actually wrong. If you look at the slopes are actually increasing from more negative to less negative, like -4, -3, -2. That's increasing. So instead of reading and trying to sketch, just do your sign analysis depending on what you're doing. You have F decreasing. F is decreasing. Okay, I could stop there, but I'm just going to go ahead. If F is decreasing, F prime is negative. Cool. The rate at which we're decreasing is decreasing. So that means the rate is like the derivative. Rates of change are slopes. So the derivatives are decreasing. That means our second derivative is negative, or my original function is concave down. Okay, this comes from our second lesson. So even though you're thinking, oh, decreasing, but we're decreasing at a lesser rate like this, turns out we are decreasing, but at a decreasing rate would look like this because the slopes would get more negative. This confuses most people. Decreasing at an increasing rate, they think this is decreasing at an increasing rate because it's like, oh, I'm decreasing faster. But it's not. It's all about the slope values increasing or the slope values decreasing. So like this is like -0.5, -1, -2, -3. Those are decreasing values. If f prime is positive, f is going up. If f double prime is 0, f prime is constant, or f has no concavity. We're kind of familiar with points of no concavity, but here the entire thing has no concavity. So I'm just increasing no concavity. That's f. And it'd be the same thing here. Decreasing no concavity. I'm not going to show them. All right, you're going to see something like this on your test, maybe on your quiz. Given the table of values, what would be an educated guess for the signs of f prime and f double prime? Okay. Well, let's look. F is increasing. Okay, I'm going to start here, and I'm going to say f is increasing. Okay, cool. That means f prime is positive. I'm halfway there. F prime, positive. But how are we increasing? I mean, let's look at some secant slopes. You know, from 1 to 2, 2 to 3. What's going on? Well, I'm increasing by 2, and then I'm increasing by 4. Okay? So my slopes are increasing. That means our second derivative must be positive. I must be concave up. That's one way to do it. The other way to do it is to just graph the points. 1, 1, 2, 3, 3, 7. And as long as you're spacing things out like fairly evenly, you could see we are increasing concave up, increasing concave up. Both work. For this table, I can see that my function values are decreasing. That means f prime's got to be negative, 7 to 3 to 1. Those are decreasing my function values. Let's look at my second derivative. Let's look at f prime. Well, my slopes are getting bigger. This is important. From -4 to -2, those are going up. which means my second derivative is positive and my function is concave up. F prime negative, F double prime positive. Not sure? Sketch. Watch. 1, 7, 2, 3, 3, 1. If you do it fairly accurately, you can see we are decreasing, but we're curving upward. Decreasing, concave up. Well, this is not a nice one. F increases, then decreases. So F prime is positive. I can't say it's until 2. I might be increasing past 5. Maybe I get to 6 at 2.1 or something. Then I decrease to get to the point of 4. All I know is F is going up then going down. If you want to check your slopes, going from positive 3 to negative 1, you would assume that your slopes are decreasing, which means your second derivative is negative. F is concave down. So taking a reasonable guess, I would say F double prime is negative and F prime changes signs from positive to negative. It's not a great example. Usually it's very clear. You're decreasing the entire time, you're increasing the entire time. So maybe this is not a great example to pay attention to. Let's look at this then. Okay, F is increasing by 2, then increasing by 2. So F is increasing, F prime's got to be positive. F double prime. Well, F prime is not increasing. F prime is constant. F double prime is going to be 0. We are going up consistently. 1, 2, 2, 4, 4, 6. We are increasing with no concavity. F prime is positive. F double prime is 0. It's your best guess. 1 to negative 1, I subtract 2 to negative 4, I subtract 3. So I know that my F values are going down. I know that my F prime values are going down. My slopes are decreasing from negative 2 to negative 3. So that means F prime's got to be negative. That means F double prime's got to be negative. F's got to be concave down. So F prime is negative, F double prime is negative. If you wanted to, you could graph 1, 1, 2, negative 1, 3, negative 4. It's tough to see, but it is decreasing concave down. Maybe it's tougher to see them than I think it is, so it's actually easier to just kind of go off of the changes. Here, I'm neither increasing nor decreasing. F is constant. F prime is going to be 0. I will have no concavity. F double prime is going to be 0 because F prime is constant. I'm adding 0. So F prime and F double prime are 0. Okay. Sketch. Look at the slopes. Look at the differences. Plus 0, plus 0 to get your signs. All right, let's do a Furl curve sketching analysis to find intervals when the following functions have specific characteristics. So I want to be able to accurately sketch this graph. You'll never be asked to accurately sketch a graph on a test question, but the way that you can show that you know what the function looks like is to answer the following questions. When is F increasing and concave down? When is F prime negative and decreasing? Very important, number 2. This is the same as F decreasing at a decreasing rate. This is the same, okay? F decreasing, F prime is negative. F prime is decreasing. F prime going down, F double prime is negative. So this is where we have to combine the last two lessons. We'll need a first derivative sign analysis. I have 3x squared minus 12x. I'll set that equal to 0 or see when it's undefined. I don't have to worry about the undefined part. I haven't had to worry about that in a while, but keep it in the back of your brain. I get 0 and 4. So here's my F prime analysis. F prime is 0 here. Multiplicities are 1. I check 5, positive, positive, positive. I know I changed signs, but you can always check. That tells me F is going up, going down, going up. Let's do a second derivative analysis. Second derivative of 6x minus 12. When is that 0 or undefined? Don't have to worry about the undefined part. That's going to be at 2. I like to put these on top of each other. 2, F double prime. I'm not going to have it factored. It's easy enough to just plug in 3. 6 times 3 is 18 minus 12 is a positive. That's negative. That's telling me F prime is decreasing then increasing, and F is concave down then concave up. I like to have it on top of each other just so I can keep track of the intervals. For question number 1, when is F increasing and concave down? Here, F is increasing and concave down. Here's where F is increasing, concave up. So increasing, concave down is just going to be x is less than 0, or from negative infinity to 0. Number 2, when is F prime negative and decreasing? F prime negative, F prime decreasing. We can see it right here. It's the same question as F decreasing at a decreasing rate. F decreasing rate would mean F prime is decreasing. We are looking for here and here, where F prime is negative and decreasing, 0 to 2. I'll put it in order. Oh, I just said I'll put it in order, and then I messed up. 0 to 2 or 0 to 2. Both of these are acceptable. Pick one way that's comfortable with you. All right. F is decreasing concave up, or F prime is positive and decreasing. This is the same question as F is increasing at a decreasing rate. If I redo this homework, I'll make sure I would change up some of the questions. All right, so combine the last two lessons. I got 18x minus 9x squared is F prime. I'll factor out a 9x. I get 2 minus x. Set that equal to 0 or see when it's undefined. I have my first derivative sign analysis, focusing on 0 and 2. This is a 0, this is a 0. I'll plug in something like 3. It's a positive times a negative, so this is a negative. And then I would change signs. The multiplicities are 1, so I got that. All right, so F prime sign analysis tells me F is decreasing, increasing, decreasing. Let's do a second derivative sign analysis. Second derivative is 18 minus 18x. Set that equal to 0 or see when it's undefined. I don't have to worry about the undefined part. I get x is 1. So I'm going to put this, you can put it next to it, but I like it on top of each other just so you kind of help with your intervals. So give myself some space at 1. F double prime signs are 0 at 1. If I plugged in something like 2, 18 minus 18 times 2 is going to be negative. I would change signs at 1. If I plugged in 0, it'd be positive 18. So this is telling me f prime is increasing then decreasing, which is telling me f is concave up, concave down. I got a min here. I got a max here. I got a point of inflection here. I got everything I need to know. I could accurately sketch the original function. I could even plug in 0, 1, and 2 to find some nice points. Have a nice graph of my original function. But what would be asked of you on a test is like this, showing you know how to accurately sketch. All right, f is decreasing. Okay, f is decreasing here and here. F is also concave up. F is concave up here. So I'm not going to include this first one. I'm just going to do where these overlap, which is negative infinity to 0. I'm not going to go all the way to 1 because f increases from 0 to 1. So this is where f decreases from negative infinity to 0, and it's also concave up. So for number 1, I have from negative infinity to 0, x is less than 0. Number 2, f prime is positive and decreasing. Let's think about it that way. F prime is positive. I got it right there. F prime is decreasing. F prime is decreasing. I got it right there. So it's like if you have all of your charts laid out, you can see where things overlap based on signs or the words. F prime decreasing, F prime positive, F prime decreasing, 1 to 2. If I said F is increasing at a decreasing rate, what you would have done is, highlighted F is increasing and then at a decreasing rate, F prime is decreasing, boom, right there. Okay. More of the same. F is increasing concave up, F prime is negative and increasing, or F is decreasing at an increasing rate. Comfortable with that being the same thing, same question. Combine the last two lessons to sign analysis. I got 20x cubed minus 5x to the fourth. I will factor out a 5x cubed. I get 4 minus x. Set that equal to 0. See when it's undefined. I'll skip that part. Here's f prime. 0 and 4. F primes are 0 there. They're going to be negative. If I plug in 5, positive, 4 minus 5 is a negative. Multiplicities are both odd, so I will be changing signs. You could also check your intervals. That tells me f is going down, going up, going down. Let's do f double prime. 60x squared minus 20x cubed. Setting this equal to 0 or c when it's undefined. Don't have to worry about the undefined part because there's no denominator. I'm just going to factor out a 20x squared. And I have 3 minus x. So 0 and 3, I will put down here. F double prime, 0 and 3. Sign analysis of f double prime. So plugging in 4 positive times a negative, that's a negative. I have zeros here, so points of no concavity. I will change signs at x equals 3. The multiplicity is 1. If I checked at 1, positive times a positive is a positive. I will not change signs at 0 because the multiplicity is at 2. I could double check that. Negative 1 squared is a positive. 3 minus negative 1 is a positive. Positive times positive, positive. All right, so that tells me f prime is going up, going up, going down. That tells me f is concave up, has a point of no concavity, so it's flattened out enough so that it's like a straight line at that point. Then it's concave up, then it's concave down. Number 1 When is f increasing concave up? When is f increasing and concave up? So I have this interval, which overlaps with this interval. I don't have it anywhere here because f is decreasing. It is also concave up, but decreasing concave up. Here I am increasing concave up. The intervals from 0 to 3. Two, f prime is negative and increasing, or f is decreasing at an increasing rate. F prime is negative and f prime is increasing. Here's f prime increasing. Here's f prime increasing. Here's when f prime is negative and increasing. Or f is decreasing at an increasing rate. So negative infinity to 0. Just making sure decreasing, this would be decreasing at a decreasing rate, or this would be f prime is negative and decreasing. Negative infinity to 0, so x is less than 0, or negative infinity to 0. All right. F is decreasing concave down. F prime is positive, means f is increasing. Positive and increasing means f would be increasing at an increasing rate. Cool. Sign analysis of our derivatives. Let's go with f prime. I have 5 times 1/5, which is just 1. So I just have x to the 4th. 3 times 1/3 is just going to be 1. Subtract 1, I get x squared. So x to the 4th minus x squared. Set that equal to 0 or see when it's undefined. I don't have to worry about the undefined part. I got x squared minus 1. Nice! Because that factors to be x plus 1, x minus 1. Or you could just like solve this set equal to 0. So negative 1, 1, and 0 is f prime. F prime zeros. Negative 1, 0, 1. F prime zeros. All right, let's plug in something like 2. I like to start on the right because it's usually obvious and it's the easiest. Positive, positive, positive. I will not change signs at 0, but I will change signs at negative 1 and 1 because of the multiplicity. So at 1, change signs. At 0, don't change signs. At negative 1, change signs. That's telling me what f is doing. F is going up, going down, flattening out, going down, flattening out, going up. I already know this is going to be a point of inflection. Like if I sketched f increasing, decreasing, flattening out, decreasing, I can see it's like my curvature changes and then increasing. So let's double check though. Let's do a sign analysis of f double prime. 4x cubed minus 2x. Great. Factor out of 2x. I have x squared minus 1. Is that right? I have 2x squared minus 1. That's right. I probably wouldn't factor this like I factored this. This I could have solved, set equal to 0. You get x squared minus 1 equals 0. You add 1, you get x squared equals 1. You square root both sides, you get x equals plus or minus 1. I'm not going to do that. I'm not going to factor, but I'm going to do that for this. I'm going to take 2x squared minus 1 and solve it. That way I know that I actually get x squared equals plus or minus root 1/2. You can leave it like that. It's important to know that root 1/2 is just 1 over root 2 because the square root of 1 is 1. And then root 2, 1 over root 2 can be rationalized to be root 2 over 2. So I've done that to get my answers. 0 and then plus or minus root 2 over 2. Now, root 2 over 2 is less than 1. This is important. It's like the square root of 1/2. Obviously, the square root of 1/2 is like going to be a value that's less than 1. 0.5 square rooted ends up being something close to 0.7. So that's important to know where things are placed, especially when you're putting intervals on top of intervals. Now, like, this should make sense. Increasing, flattening out, decreasing, flattening out, decreasing, flattening out, increasing. You can see it's like, okay, point of inflection here at 0, but there's also a point of inflection here and a point of inflection here. These are going to be occurring at these root 2 over 2s, the square root of 1/2. Okay. So this helps us, be very exact with the curvature and the shape of our function, where our curvature changes. And it's easy to find just by doing a sign analysis of a second derivative. I'm going back into this second derivative. I could go ahead and assume that we're going to change signs because, like, if I did write this in a factored form, like the multiplicities would be 1. But, like, let's pretend we don't know how to do that. Let's just check all of our signs and all of our intervals. Though it would be tough here, but let's see. Let's plug in something like 2, positive. This is going to be bigger than 1, so positive. What do I plug in? I don't know, something close to 0. Let's think about plugging in something close to 0 but positive. That would be positive. Something very small squared is still going to be very small. Times 2, probably still going to be very small. It's probably still going to be smaller than, it's definitely going to be smaller than 1. So though this is a positive, this very small number minus 1 is going to be a negative. So that's a negative. Okay? Now, if I plug in something very, very small that's negative, this is a negative. But this small negative number squared times 2 is a very small positive minus 1. It's going to be a very small negative. So I have a negative times a negative now in this interval. That turns into be a positive. This is the whole increasing concave down, decreasing concave up, decreasing concave down, decreasing concave down, decreasing concave up, increasing concave up. It's like, this is a tricky one. And if I plug in something like -3, negative, this would be a positive. Oh no. Gotta plug in my slate. Cool. So this is a negative. So that's telling me when f prime is decreasing or increasing. That's telling me when f is concave down, concave up. Okay. Number 1, the question was, when is f decreasing and concave down? Here is when f is decreasing. It's when f prime is negative. Decreasing, concave down would be here overlapping with this. So it would be just 0 to root 2 over 2. Number 2, when is f increasing at an increasing rate, or when is f prime positive and increasing? When is f prime positive and increasing? There's f prime increasing, its derivative is positive. F prime is positive and increasing here from 1 to infinity. Okay? Tricky stuff. Requires practice, especially even just to like set up your intervals like on top of each other and then look at when things overlap. Jerks. Who wrote this question? Mr. Messer, why did I write this question? Because I want you to practice your derivative rules. That's why. F prime's easy to analyze. Like 2x minus 3, I have to set that equal to 0. Add 3 divided by 2 is 3 halves. This is going to be a root at -1. and then I have 3/2. Fantastic. Okay. I think you had this on a previous homework. Would not will change signs at 3/2 because the multiplicity is 3. Will not change signs at -1 because the multiplicity is 2. Plugging in something like 5, obviously positive. 2 times 5 minus 3, positive, cubed, positive. 5 plus 1 squared. This is always going to be positive. So that's a positive. Will change signs, will not change signs. So F is going to be decreasing, flattening out, decreasing, flattening out, increasing. All right, let's go. How do I take this derivative? Well, it's a product with some chains. Yep, let's see if this works out. Okay, so product rule. Derivative of the first times the second. So the derivative of the first has an outside and an inside. Fortunately, it won't be that bad because the inside's derivative is just 1. So I'll have just 2 parentheses times 1. So the derivative of first is 2x plus 1 to the first times 1. That's the derivative of the first times the second. Plus derivative of the second. Now the derivative of the second will be different than maybe what we expect, because if we do use the chain rule, we'll have 3 parentheses squared times 2. The 3 times the 2 multiplies to be a 6, so I'd have 6. 2x minus 3, what starts in the parentheses stays in the parentheses. Don't forget about the squared. This is the derivative of the second times the first, x plus 1 squared. To solve this set equal to 0, we need to factor. You could write it as 2, I don't know, let's use a and b. 2ab cubed plus 6b squared a squared. Maybe that helps you. Because what I can see is I can factor out a 2, 1a, and 2 b's. Cool. What's left over after I factor a 2a and b squared will be 1b from here and 3a from here. So the 2 divided by the 6, 1a pulled out of this gives me 3a. Now, I actually can solve this after a little bit more simplification. 2x plus 1, 2x minus 3 squared. This is 3x plus 3. 3x plus 2x is 5x. Negative 3 plus 3, that's 0. That's it. Just happens to work out like that, so that there's not another number. Okay, giving me solutions at -1, at 3/2, and at 0. Okay, so over here, I have -1 still. I have 3/2 still. Line them up, but I also have 0 because of the 5x. These are all zeros. The sign will not change at 3/2. The signs will change at 5x, at 0, and at -1. The multiplicity of the 2x minus 3 is 2. That's good to know. If I plug in something like, 5, positive, 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 positive. I can double check. Plug in something like 1, positive, positive, a negative squared, which is a positive, positive. So positive, 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 positive. Or look, I do not change signs at 3/2 because the multiplicity of that root is 2. Do not change signs. I will change signs. I will change signs at 0 and at -1. Fantastic. Okay, we finally got there. That means f prime is going up, going down, going up, going up. That means f is concave up, no concavity. Concave down. So we have a point of inflection here. No concavity, concave up, point of inflection. No concavity, concave up. We don't have a point of inflection at 3/2. We have a point of no concavity. Where is F increasing, concave down? F is increasing, concave, never. Doesn't happen. I feel like I probably asked this question without doing it first. So I'm like, I bet you it's going to be increasing, concave down somewhere. Turns out, nope. F prime negative and decreasing. That's the same as F is decreasing at a decreasing rate. F prime negative and decreasing. F prime negative and decreasing is just from -1 to 0. I think I've been listing it off with inequality notation first and then switching it up. Cool. Okay. Pay attention to this guy. Okay, this is what everybody freaks out on this question. Okay. The question is, what must be true? Must. Must. Always. Always. Here's what happens for you kids. Okay. And what hurts us is the table problems we did before, where I told you, yeah, go ahead and sketch. Go ahead and sketch. If you sketch, you got 110, 215, 317, 412, 510. Okay? And you're like, oh, it looks like we're like increasing concave down, and then we're decreasing concave up, right? That would be what it could be. Could be this. Could be. Must it be that? Well, let me give you another sketch. Boom, 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 boom. Ready? Let me connect these points to give you another could be, the graph of F. Whee! Boom. That's a function. That function has those points. Could the function look like that? Sure. I don't know. This is important. The questions, all these questions are about what must be true. Okay? Must F prime be positive between 1 and 3? Well, it could be. It could be that F is increasing everywhere. Must it increase everywhere between 1 and 3? No, it doesn't have to be. It could be. Must it be? No. No, could be. Must the second derivative be negative? Must you be concave down from 1 to 3? Oh, you could be. Could be. Must you be concave down between 1 and 3? No. No, because here's a situation where I'm not concave down everywhere. So no. Must we have a horizontal tangent? Well, honestly, like both this one and this one don't have horizontal tangents. I drew this with a sharp point, which means the derivative is undefined. And this one, we're increasing at 3. Obviously, it's not going straight through the points, but you get my drift. So, like, must the derivative equal 3? No, of course not. Must the second derivative be positive between 3 and 5? Well, between 3 and 5, it could be positive. Sure, it could be. Must it be positive? No, it doesn't have to be positive. Must be positive. We don't know what the function looks like. So we don't know that this must be the case. Derivative equals 0 for some x between 1 and 5. Actually, hold on. Pause a second. I told you that the function is twice differentiable. Twice differentiable just means like it's very much differentiable, which means like I do not have a sharp point. You're not allowed to have a sharp point. So let's just assume you have a nice smooth curve there. Okay, cool. Now here's where musts come through. You guys know the mean value theorem? This is a nice little review of lesson one, and this is getting ready for your test questions. Okay, the mean value theorem said if your function is differentiable and it has 2 points, you must have a location where your tangent slope is parallel to or equal to your secant slope. No matter how I draw my function, whether it's this way, or any other way, I find that the secant slope for all of my graphs between 1 and 5 is 0. Because the secant slope is 0 and because the function is differentiable, the mean value theorem works. Since the secant slope is 0, I must always have at least one location where our tangent slope is 0 somewhere in our interval. Theorems are musts. Intermediate value theorem is a must. Is there an intermediate value theorem? No, but I'm going to throw one in there. Must there be a solution f of x equals 14 somewhere between 1 and 5? Yeah, sure. Because 14 is between 10 and 17. You're going to have some point somewhere where you have the y coordinate of 14. No matter how you draw it. Must there be some solution to this equation? Yes. Why? The intermediate value theorem. Theorems are musts. Derivative signs for tables are maybes, could be's. Okay? All right, let's get to the graphs. Fun stuff with the graphs. We need a sign analysis of f prime, as well as a sign analysis of f double prime. Combining those will answer our questions. Okay. Ready? F prime signs. What do I have? I have f prime. I will look at the y values of f prime to figure out the signs of f prime. F prime will be negative until -3, positive until 2, negative after that. That means f is going to decrease, then increase, then decrease. It will flatten out at these two x locations. F double prime. Two ways to do it. You can either look at when, and I like to see some people do this, like you can either look at when f prime is increasing and they drew arrows. It's like f prime is going up, then f prime is going down. And they're like, okay, f prime is going up, then going down. That's one way you could do it. Or you could say, let's look at some tangent slopes. Slopes of f prime are f double primes, right? Positive tangent slopes, they're positive. I don't care if they're lesser, more than, they're just positive, and then they change to negatives. F double prime signs are positive and then negative. It's got a 0 at 0. That's when we change from increasing to decreasing. That's when we flatten out. That is how we can get that. F is concave up, then concave down. All right. When is F increasing and concave down? When is F increasing here and concave down here? So I'm looking at this interval here when we are doing both. That's from 0 to 2. When is F prime negative and increasing? That's the same as when F is decreasing at an increasing rate. decreasing at an increasing rate, or f prime negative and increasing. Here's f prime increasing, here's f prime negative and increasing. Right there. So from negative infinity to negative 3. Cool? Cool. Here's another graph of f prime. Okay? So look at y values. Look at slopes of f prime or whether f prime is increasing or decreasing. Start with the y values. Y's are positive. Y's are 0. Y's are negative. F prime's y values are positive until negative 2, where they're 0. But then they go back to being positive all the way until 1. Then they go to negative until 3, and then they're back to being positive. F prime is going down, going up, going down, going up, going down, going up until 0. It went down until negative 2. Going down until 2. Going up after that. Okay, that's the same as looking at the slopes of f prime. Slopes are negative, 0, positive, 0, negative, 0, positive, negative, 0, positive, 0, negative, 0, positive. Yeah, of course, has to be. Slopes are positive. F prime slopes are positive. That means f prime must be increasing. Yeah, I see both. That tells me f is concave down, concave up, concave down, concave up. You produce this, you're ready to answer any question. When is f decreasing, concave up? When is f, oops, I forgot, f increasing, increasing, decreasing, increasing? When is f decreasing and concave up? F is decreasing here. It is concave up and decreasing here. 2 to 3. Can you get this answer by just looking at the graph? Sure. Sure. You can understand how the sign charts are created, know for what you're looking for. F is decreasing, F prime is negative. Okay. F prime is negative. You're looking just in this interval. F is concave up, F double prime is positive, or F prime is increasing. Boom, right there. You can get that. You can get that. If you can get that, get it. If you can't, do the sign analysis. When is F prime positive and decreasing? When is F prime positive and decreasing? I mean, literally, you could just look at the graph. When is F prime positive and going down? So actually, I might have missed one if I used the table. I didn't look at, oh, here's positive and going down. Here's positive and going down. Probably the better question to ask is not this, but when is F increasing at a decreasing rate? I probably would ask that question. And then that would have to say, oh, F is increasing because F prime is positive. At a decreasing rate, F prime is decreasing. So I got less than 2 and 0 to 1. Let's write this in inequality notation. Less than 2, less than negative 2, and 0 to 1. Both of those intervals. Negative infinity, negative 2, 0 to 1. Either of those. How many critical points, relative extrema, and points of inflection does f of x have? All right, critical points when f prime is 0. Doesn't have to change sign. I have a critical point at x equals -2, 1, and 3. Critical points are all about the first derivative. I'm not going to include 0 and 2, which come from the second derivative. Those are not critical points. Those are possible points of inflection, but we don't call them critical. Relative extrema. X equals 1 is a max. X equals 3 is a min. Why f prime changes signs at those locations. We have one of these neither situations. It's a critical point, but it's not a max or min. Points of inflection, we change concavity at -2, 0, and 2. All right. Getting there. All right. Sharp points. Oh no. Sharp points. I have to do something different. Nope. Nope. Don't do it. Don't freak out. Don't freak out. Just do what we've been doing. Just go off of what you have. F prime. This is F prime. Okay, that's good to start with. So F prime signs based on the Y values. F prime is positive until -3. It is negative Y values. It's got a 0 here. Negative Y values until -1. It's got positive Y values until 1, but it's positive values after 1. Cool. That tells me about F. F's got to be going up, going down, going up, going up. Yeah, but Mr. Messer, sharp points, sharp points. Well, watch. Start with F prime. Going down, going up, going down, going up. Let's just start with that. Going down until -2. Put that in the right spot. Going up until 0. Going down until 1. Put that in the right spot. Going up after that. If you looked at slopes, negative slopes until -2. Positive slopes, negative slopes, positive slopes, positive slopes, negative slopes, positive slopes. So yeah, that checks out. Okay. But what is the slope of f prime at -2? It's undefined. It is not 0 because it's a sharp point. It's undefined. But guess what? We don't care. It's still going to be a point where we change concavity. May look like a sharp point. May not. Who knows? It doesn't matter. If you do the analysis correctly, you know that -2, 0, 1 are all points of inflection. We go from concave down to concave up to concave down to concave up. How many critical points do we have? We have 3. X equals -3, -1, 1. Extrema, x equals -3 is a min. It's a max because f goes up and down. X equals -1 is a min. X equals 1 is a neither. So it's not an extrema because it goes up, flattens out, goes up. How many points of inflection do we have? We have 3. We change concavity here, here, and here. Do I care about those sharp points? No. There's a test question out there where there's a sharp point and freaks everybody out, and they're like, no, I can't do it. It's like, no, it's fine. It is. -2, 0, and 1 are points of inflection. Don't worry about it. The analysis shows that it is. Must be. But I can't. No, it's fine. It's fine. Maybe the original graph looks like sharp points at certain locations, but it just works out. Okay? Don't worry about it. When is f increasing and concave down? F is increasing, concave down. Increasing, concave down here, increasing, concave down here. Should go down here. You could go to the graph and say f prime is positive and decreasing. There, there. I could just look at the graph and get my answer. F prime is positive, F double prime is negative, or F prime is decreasing. F prime is positive, F double prime is negative. F prime is positive, F double prime is negative. Do you have to do this entire thing? No, no. If you've done enough of them, I can get my answers. Now I give you the graph of F. When is F prime positive and F double prime positive? What? Well, F prime positive means F must be going up. F double prime positive means F prime must be increasing, or F must be concave up. I change this question into, hey, this is the graph of F. When is F increasing, concave up? Now, let's just assume there's a point of inflection here. You'll be told where the points of inflection are on your quizzes and on your test. Here I'm concave up, here I'm concave down. When I increasing and concave up would just be this interval right there. That's the piece of the function where both of those things are happening from 0 to 1. Where is f prime positive and decreasing? Okay. Again, f prime positive means f going up. F prime decreasing means f concave down. Does it mean that f double prime is negative? Sure. But since I have the graph of f, all I need is to look at when f is going up, but is concave down. Going up, concave down. Right there, 1 to 2. Order from least, which is like a negative, most negative, to the greatest, most positive. F of 2, F prime of 2, and F double prime of 2. What? Well, you see that F of 2 right there? I don't know. It's a Y value. It's a positive Y value. F of 2, I don't know. Just pretend it's like 3. Pretend that's 3. Okay. What's F prime of 2? Okay, well, the slope of the tangent here would be F prime. Well, that looks like a horizontal tangent. I'm going to say that's 0. What the heck is F double prime of 2? Oh, you know what? F is concave down, right? Oh, that means F double prime's got to be negative. So F double prime of 2, some negative number. I don't know, negative 1. Order from least to greatest? Oh, F double prime of 2 has got to be less than F prime of 2, because this is a negative and this is 0, which has got to be less than F of 2. Oh, calf time? I totally forgot about calf time. Oh, brother. I'm not even done with this. All right, well, let's figure this out. All right. F prime is negative, F prime, negative. F's got to be going down. F double prime negative means F prime is decreasing, which means F is concave down. When is F going down, concave down?
What?
Going down, concave down. That's it. Here's going down, concave up. Here's going up, concave down, going down, concave down, going down, concave up, going up, concave up. So just from negative 1 to 0. F prime positive and decreasing. If F prime is positive, F is going up. If F prime is decreasing, F must be concave down. F double prime must be negative. Going up, concave down. Going up, concave down. When are we going up, concave down? Going up, concave down. Right there. Going down, concave up, going up, oh, no, I want going up, concave down. Yeah, going up, concave down. That's just it. -2 to -1. Order from least to greatest at -1, 2, 3, 4. All right, cool. F of -4, it's 0. That's the y value of f. F prime, I know that's a negative value because the slope of the tangent is negative. F double prime is positive. How do I know that? Because f is concave up. So if I'm ordering from least to greatest, f prime of -4 will be less than f of -4, which will be less than f double prime of -4. I have improved on the way I'm doing this stuff from past years to hopefully make things more understandable for you guys. And hopefully this homework was not too crazy, just a combination of the last two lessons. Good luck out there.